the past few years, additive manufacturing has come a long way. For instance, Markforged's CFF process allows us to print strong, in-use parts by reinforcing plastic prints with continuous fibers. With SOLIDWORKS simulation, you can use tools you already have to design and implement functional 3D printed parts more efficiently. In this example, we will print a replacement tailwheel arm for an SZD-45 Ogar powered glider. The part needs to be strong enough to sustain significant torsional and bending loads, but needs to be as light as possible to prevent issues with the aircraft's flight performance. The first thing that we need to do is set up a topology study with the part that we want to print. We use 6061 aluminum to approximate the behavior of a carbon fiber reinforced part, as the stiffness and strength are close enough for our purposes. Now we need to define our loads and fixtures. We will define a remote load on the bearing surfaces, allow the pinhole to rotate, and put a roller on the surface under one end of the part. Since this part sees multiple load cases, we will use the load case manager to vary the position and magnitude of the remote load to generate a shape that accounts for all loading conditions, instead of running several different studies and superimposing the results manually. This saves us time, improves the accuracy of our solution, and removes the possibility of human error. To ensure that we get a useful result, we will use the minimum reinforced member width from the Markforged Composites Design Guide to define a thickness control for the model and a few preserved regions on functional surfaces. As for the goal, we are aiming for the best stiffness to weight ratio so that we can create a fiber layout that is both strong and efficient. This will provide a useful result that takes the CFF process constraints into account and prevents us from extrapolating our results or running our study multiple times. Once our study is set up, we can mesh the model with a high-resolution mesh and run the study. We can use these results to modify our part geometry if necessary. Typically, we would rely on experience to determine where we could remove material, but topology results make these decisions easier and more concrete. For geometries that are hollow, it is assumed that these spaces can be filled with a lattice structure infill and left alone in the model. Once any necessary changes to the model are made, we export it as an STL file and import it into Eiger. Here, we use our topology results to guide the placement of fiber reinforcement into the part. We will add some additional reinforcement to further guard against part failure. Without this study, we would simply have to let theory and experience guide us in placing fiber reinforcement, creating more work and possibly costly failures. After we print our part, perform post-processing operations, and test it to confirm our results, the part is put into service. Traditionally, we would wait for a machine shop or service bureau to manufacture our part, which takes days to weeks. But with additive manufacturing, we simply print our part as soon as it's ready, drastically reducing our lead time. Take your implementation of additive manufacturing to the next level with SOLIDWORKS simulation. These tools enable you to take full advantage of what additive manufacturing has to offer your organization. To learn more about Markforged, design for additive manufacturing, other simulation capabilities, training on these tools, or the glider tailwheel arm that we printed, click the link below and check out other videos.